In this paper, we present an approach for fast subspace integration of reduced coordinate nonlinear deformable models that is suitable for interactive applications in computer graphics and haptics. Our approach exploits dimensional model reduction to build reduced coordinate deformation bases for models with complex geometry, such as this bridge. We exploit the fact that model reduction on large deformation models with linear materials result in internal force models that are simply cubic polynomials in reduced coordinates. Coefficients of these polynomials can be precomputed for efficient runtime evaluation. This allows us to simulate nonlinear dynamics with fast implicit Newmark subspace integrators with subspace integration costs independent of geometric complexity. Our method is fast enough to support force feedback rendering of detailed models undergoing large deformations. For example, using a phantom haptic interface, the user can feel the response of the massive bridge model when pushing a sphere against it. Both nonlinear subspace integration and reduced coordinate collision detection using bounded deformation trees are performed in less than a millisecond. In our work, we present two methods for generating a subspace basis for nonlinear deformations. The first approach uses modal derivatives to significantly extend linear vibration modes into the nonlinear regime. Modal derivatives specify how linear vibration modes change along the nonlinear deformation manifold and are easily precomputed. We then use mass-based principal component analysis of all modes to extract our subspace deformation basis. Because subspace integration costs are independent of geometric complexity, we can integrate the subspace dynamics of very complex structures at modest costs. Although our modal derivative models are computed about the rest pose, they nonetheless provide a rich basis for large deformations. Although our reduced force polynomials are precomputed, it is possible to modify material parameters at runtime. Our second approach generates a subspace basis from user-specified motion. We have investigated an interactive sketching approach wherein the user first interacts with a fast linear model, while user-applied forces are recorded to disk. An offline static solver then computes accurate nonlinear shapes corresponding to a subset of these static force loads. Mass-based PCA then produces a shape basis suitable for runtime simulation of nonlinear shapes similar to those sketched. Additional sketches can be used to refine the motion basis as desired. Although our subspace integrator does not support nonlinear materials, it provides inexpensive large deformation dynamics for real-time applications. For example, in surgical simulations, large deformations are quite common, but only a small fraction of computation time can be devoted to real-time deformations. In summary, our approach makes it possible to precompute fast reduced coordinate force models suitable for implicit Newmark integration of geometrically nonlinear deformable models.